Hi, I welcome you all to this session on thermal expansion. And taking you on this journey is Dr. Yunus Jerusha, an assistant professor of physics. There are so many objects around us which cause us to puzzle. Let us see what some of those are and try to find explanation as to why they are so. Why glassware used in kitchen are not made up of thin glasses? Why one end of a steel bridge is not fixed in concrete? Why telegraph and electrical lines are never hung tautly between poles? Why space is provided between rails and bridges? Why a tight glass stopper or a metal screw cap can be opened by heating them? The answers for all these can be found by looking at a few topics in detail. What is thermal expansion? Why heating leads to thermal expansion? Does thermal expansion occur in liquid also? Does thermal expansion take place in gases also? In daily life, we would have seen these: the gap in bridges, the gap in railway tracks, thick glassware in kitchen, one end of a bridge not fixed to the ground by means of concrete, and loosely hung telegraph and electrical lines. What is thermal expansion? The change in temperature of a body causes expansion or contraction of that body. Most of the substances expand on heating and contract on cooling. Thermal expansion occurs in solids, liquids, as well as in gases. Let us see a few examples. Firstly, in solids. These are pipes which carry hot liquids. They are bent in shape in order to accommodate for the thermal expansion which occurs. The air gap, which is present in an aircraft's window, is also present in order to accommodate for the thermal expansion which occurs when the aircraft travels at high speeds. Secondly, thermal expansion in liquids. Here we have a thermometer where mercury is present. Mercury, being a liquid, expands and there is a change in the level of the mercury indicating the current temperature. A hot air balloon is a good example for thermal expansion which occurs in gases. Thermal expansion, as we've just seen, occurs in solids, liquids and gases. And depending along which dimension thermal expansion occurs, we have three types of thermal expansion, namely linear expansion, superficial expansion and cubical or volume expansion. Solids, being regular in shape, have the three types of expansions to occur in them, whereas liquids and gases, which have loosely bound particles, have only the cubical or volume expansion to occur in them. Linear expansion occurs when there is a change or expansion occurring along one dimension. Superficial expansion is the expansion where we have a change in the area to occur, and cubical expansion is the expansion where we have a change in the volume of the material to occur. This slide gives us a visual representation of the linear, the superficial and the cubical or volume expansion. Let us first see what exactly is linear expansion. It is a change in length along one dimension over the other three dimensions and is proportional to the original length. Here we assume that the effect of pressure is negligible. The coefficient of linear expansion is denoted by alpha and it is defined as the increase in length per unit degree rise in temperature of that substance. It's given by alpha is equal to an increase in length divided by the original length into the rise in temperature. If L1 stands for the original length before thermal expansion and L2 is the length after expansion, L2 minus L1 gives us the increase in length. The original length is L1 and the rise in temperature is given by T2 minus T1, where T1 is the temperature before thermal expansion and T2 is the temperature after thermal expansion. Therefore, alpha is given by delta L divided by L1 into delta T, and the unit being Kelvin inverse or per degree centigrade. Let us analyze linear expansion by means of a realistic problem. The main span of San Francisco's Golden Gate Bridge is 1,275 meters long at its coldest. The bridge is exposed to temperatures ranging from minus 15 degrees Celsius to 40 degrees Celsius. What is its change in length between these temperatures? Assume that the bridge is made entirely of steel. The linear expansion coefficient of steel is given by 12 into 10 power minus 6 per degree Celsius. We are going to use this formula. Delta L is equal to alpha L into delta T, where alpha is given by 12 into 10 power minus 6, L is given by 1275 and delta T ranges from minus 15 to 40 degrees, which is 55 degrees Celsius. So we substitute in the formula and we obtain the final answer as 0.84 meter. This seems quite insignificant, but it is really quite large when compared to the actual length of the bridge. And since this 0.84 meter is spread over several expansion joints, the expansion of each joint is very small, and that is why the Golden Gate Bridge still stands strong and tall for all to see. Linear expansion coefficient is an intrinsic property of every material and it varies from one material to another. The rate at which a material expands purely depends on the cohesive force between the atoms. Cohesive force is the force that binds two or more atoms together, and this cohesive force is the force which resists the atoms from getting separated from each other. More the cohesive force, lesser will be the expansion of the material. This animation clearly shows us which is the material having a higher expansion coefficient and which has the least expansion coefficient. Alumina here has fine grains and has a lesser expansion coefficient. Therefore, this alumina is used in refractories and as crucibles in thermal experiments. Whereas stainless steel, which is elastic in nature, has a higher thermal expansion coefficient and is used for building materials. The outcome of advancement in science and technology are immense. To march with this rapid growth in industrialization and constructions, one needs to be sure about the usage of the materials. Starting from constructing a building till constructing a satellite, materials used act as a backbone. Higher linear expansion coefficient materials such as metal alloys are strong in nature and therefore are used in building firm structures. Railroads and bridges are prone to expansion and contraction depending on the climatic conditions, and therefore expansion joints are used in order to make them firmer. Metal hot water heating pipes must be bent and should not be made long and linear. Scanning electron microscopes need to detect minute changes in temperature to change their position relative to their focus point. Liquid thermometers use mercury or alcohol, so they flow in only one direction as the liquid expands due to temperature changes. Each of these examples demonstrates how materials expand in length under heat. The next type of thermal expansion is given by the superficial expansion. It is defined as the increase in surface area of the solid on heating and is proportional to the surface area. It is measured in terms of the coefficient of superficial expansion denoted by beta. This is defined as the amount by which unit area of a material increases when the temperature is raised by 1 degree. Mathematically, we write beta to be increase in area to the original area into rise in temperature. The increase in area is given by A2 minus A1, where A1 is the original area before thermal expansion and A2 is the area after thermal expansion has occurred. The rise in temperature is given by T2 minus T1, where T1 is the temperature before thermal expansion and T2 is the temperature after thermal expansion. We sum it up as beta is equal to delta A divided by A1 delta T with the unit Kelvin inverse. A classical example for superficial expansion is the ball and ring experiment. Before the heating of the ring, the ball cannot be taken out of the ring. But after the ring is heated and undergoes expansion, the ball easily slips out of the ring. Let us try to relate the two phenomena which we've just seen, the linear expansion and the superficial expansion by means of their coefficients. For isotropic materials and for small expansions, the linear thermal expansion coefficient is 1/2 of the area coefficient. Let us try to prove this. Consider a square of length L. On heating, this square L undergoes an expansion and its length increases to L plus delta L. Therefore, there is a change in area also. The original area for a square A is given by L square, and after thermal expansion the new area is denoted by A plus delta A, and since the length of this new square is L plus delta L, it becomes L plus delta L the whole square, and on expanding it we have L square plus 2L delta L plus delta L square. Delta L being a very minor change, and higher order terms of this minor change is going to be extremely small, and we neglect the delta L square term. Therefore, A plus delta A becomes L square plus 2L delta L. And we are going to now look at the second term. The second term is 2L delta L. We multiply and divide this second term by L. When we multiply by L, L and L gives us L square, which is A. And therefore, the second term changes as 2A delta L by L. Also, look at this equation. On the left hand side, and on the right hand side we have A. They get cancelled out, and therefore delta A becomes 2A delta L by L. When we cross multiply and bring A, which is there on the right hand side, to the left hand side, we have delta A by A equals 2 delta L by L. Delta A by A is nothing but beta, and delta L by L is nothing but alpha. Therefore, beta is equal to 2A, or alpha is equal to beta by 2. And we have proved that the linear expansion coefficient is 1/2 of the area coefficient. Here is an interesting question. Imagine that we have a rectangular sheet of metal with a circular hole in the middle. If the metal is heated, we can guess that the piece in general will get larger due to thermal expansion. Now, what is going to happen with the circular hole in the middle? Is the hole going to be larger or smaller? Imagine that we have a similar metal sheet, but without a hole. Draw an imaginary circular line representing the circular hole in the situation. How does this imaginary circle change as the metal is heated? Did you guess? Yes, it will get bigger. Therefore, you can guess that the hole will get larger. Now for some applications of superficial expansion. 1. Fix an iron rim on a cartwheel. Remove the tight metal cap of a glass jar. And thirdly, bimetallic thermostats as in a fire alarm, electric iron or water heaters. Let us look at the third type of thermal expansion called as cubical expansion. This cubical expansion, as we've seen, occurs in solids, liquids as well as in gases. The definition for cubical expansion is: the increase in volume is directly proportional to the initial volume of the material and rise in temperature. It is measured by the coefficient of cubical expansion denoted by gamma. The definition for this is: it is the increase in volume per unit degree rise in temperature of that substance. Mathematically, we write gamma as the ratio between the increase in volume to the original volume and the rise in temperature. The increase in volume is given by V2 minus V1, where V1 is the volume before thermal expansion occurs and V2 is the volume after thermal expansion occurs. The rise in temperature is given by T2 minus T1, where T1 is the temperature before thermal expansion and T2 is the temperature after thermal expansion. We have delta V, which is the increase in volume, and the rise in temperature is denoted by delta T. Therefore, gamma is equal to delta V by delta T into V1 with the units Kelvin inverse or per degree centigrade. We are now going to prove that there is a relationship between the linear thermal expansion and the cubical thermal expansion. For isotropic materials and for small expansions, the linear thermal expansion coefficient is 1/3 of the cubical thermal expansion coefficient. For this, we consider a cube of length L. The volume of this cube is going to be L cube. On heating the cube of length L, it expands in its volume and the length of the new cube is going to be L plus delta L. Accordingly, its volume is going to be L plus delta L, the whole cube. Let us prove this mathematically. The original volume V is equal to L cube. The new volume is V plus delta V, as told, is L plus delta L the whole cube. Expanding, we have L cube plus 3L square delta L plus 3 delta L square L plus delta L cube. The last two terms contain higher order terms of delta L, and therefore delta L being small, we ignore the last two terms, and therefore we have V plus delta V to be equal to L cube plus 3L square delta L. We substitute V for L cube in the next equation, and for the second term 3L square delta L, we multiply and divide by L. On multiplication, in the numerator we have L cube, which is V. Therefore, V plus delta V now becomes V plus 3V delta L by L. And V, which is there on the right hand side as well as on the left hand side, get cancelled out. Therefore, on cross multiplication of the left out terms, we have delta V by V to be equal to 3 delta L by L. As we all know, delta V by V is nothing but gamma and delta L by L is alpha. On substitution, we have gamma, which is the cubical thermal expansion coefficient, to be 3 times that of alpha, the linear thermal expansion coefficient. And we have the final expression alpha to be equal to gamma by 3, which proves our relationship. Let us look at another real-time situation. Suppose a 60-liter steel gasoline tank is full of gas, so both the tank and the gasoline have a temperature of 15 degrees Celsius. How much gasoline has spilled by the time they warm to 35 degrees Celsius? Given the cubical expansion coefficient of gas is 915 to 10 power minus 6 per degree Celsius, and the cubical expansion coefficient of steel gamma S is 35 into 10 power minus 6 per degree Celsius. Let us try to find the solution. We find out the increase in volume of the steel tank given by delta Vs equals gamma S Vs delta T. The increase in volume of the gasoline delta V gas equals gamma gas V gas delta T. Tank and gasoline increase in volume, but gasoline increases more. So the amount spilled is the difference in their volume change, which is given by V spill equals delta V gas minus delta Vs. We combine the above three equations and we have V spill to be equal to gamma gas minus gamma S V delta T. Substituting the values, we obtain V spill, which is the amount of gasoline spilled due to expansion, to be 1.1 liter. This amount is significant, particularly for a 60-liter tank. And why this is significant is that sometimes when we try to compress this gasoline into the tank might get ruptured. And when there is rupture of the tank, it leads to life-threatening situations. Therefore, in order to avoid such kind of a situation, these tanks have small air gaps or there is an expansion tank to prevent this excess spillage. A few applications of thermal expansion in liquids. Rise in the level of mercury and alcohol in thermometers. Automobile engine coolant used in the automobile to avoid the overheating of the engine, and the natural cooling of water, which is a prerequisite for the existence of aquatic life forms. The natural cooling of water is due to the anomalous expansion of water. The density of water increases as the temperature increases from 0 degrees Celsius to 4 degrees Celsius. The density again decreases as the temperature is increased further from 4 degrees Celsius. This odd behavior is shown in the graph. The density of water is thus maximum at 4 degrees Celsius. During winter, the surface air is colder than the water in the lake. As the surface water is cooled, it becomes denser and sinks to the bottom of the lake. Surface water cannot possibly be cooled to 0 degrees Celsius without first being cooled to 4 degrees Celsius, and water at 4 degrees Celsius cannot remain at the surface for further cooling unless all the water below is at 4 degrees Celsius. Surface water at 4 degrees Celsius will be denser and will sink before it can be further cooled. So, before any ice can form, all the water in the pond must be cooled to 4 degrees Celsius, and then the surface water is cooled to 3 degrees, 2 degrees, 1 degree and 0 degrees Celsius without sinking. Then ice can form. This behavior is known as the anomalous expansion of water. Let us look at this in a microscopic scale. At 10 degrees Celsius, looking at water closely, it is observed it has loose hydrogen bonds and therefore the density is high. Thus, water at 10 degrees Celsius sinks down. Looking at ice, which occurs at 0 degrees Celsius, it forms a rigid structure, a perfect lattice structure where there is lot of open space, and this leads to the density being less. Therefore, ice floats on the surface at 0 degrees Celsius. What you are about to see is the popping of corn at extremely high temperatures. This is due to the thermal expansion of steam within it. When gases are heated, pressure and volume change. Gases have large thermal expansion because of the large intermolecular distance between the molecules of the gas, and this is what causes the thermal expansion in gases. There are two types of thermal expansion in gases. One is the volume expansion of gas, and secondly, the pressure expansion of gas. The various applications of thermal expansion in gases are the hot air balloons and the popcorn which we just saw. I would like to list out a few more applications of thermal expansion: buckling, expansion gap or joints, anti-scalding valves, bimetallic strips and thermostats, expansion of holes which is useful for the mounting of train tires, and aircraft expansion. Aircrafts expand due to extreme heat caused by friction when they travel at high speed. They expand by nearly 15 to 25 centimeters, and earlier designers used to keep rollers to isolate the main cabin from the body. Otherwise, there would be a ripping apart of the aircraft mid-air. A few more applications are given in the links which are shown here. If time permits, kindly do watch those. A current, imminent and dramatic impact is the sea level rise due to thermal expansion. Please watch this video to give you an idea as to how this climate change has caused the sea level to rise. This is an animation to show you how much of Chennai is going to go underwater by 2050. Let us all save the earth from this climatic change. Thank you for your patient listening. You can have your popcorn now.